Hello and welcome. In this video, we'll solve the exercise 25, 26 and 27 from the chapter 3 of the book Contemporary Abstract Algebra by Joseph A. Gallian. The statement of question number 25 is, if A belongs to general linear group of 2 cross 2 matrices where entries are from the real number R, this is general linear group, and this A is a matrix that is 2 cross 2 with the entries from real numbers, and if the order of A is finite, order of A mean in a group, the order of an element mean the smallest positive integer, such that if we take that integer as a power of that element, we will get identity. So the statement is that if A belongs to general linear group of 2 cross 2 matrices from and the entries are from the real numbers, and the order of A is finite, then what can you say about the determinant of A? So this is the question. Let's solve the question. Since the order of A is finite, say it is n, this means A trace power n is the identity matrix. Okay. Also, we know that the determinant of A trace power n is actually equal to the determinant of A whole trace power n. Okay. Now, since A trace power n is identity, this means the determinant of A raised to power n is determinant of identity, and we know that the 2 cross 2 identity is 1 0 0 1 and its determinant is only 1. Okay, this means the determinant of A trace power n is equal to 1, and also this can be written as, using this rule, determinant of A whole trace power n is 1. Okay, if we consider, let determinant of A to be x, then we get that x raised power n is equal to 1, and this means x raised to power n minus 1 is equal to 0. So the solution of this equation is actually the nth roots of unity, and if this n is odd, then x is equal to 1 is the only real root, and if n is even, this means x is equal to plus minus 1 are only real roots. So the conclusion is that the determinant of A, because we put this determinant of A is equal to x, determinant of A is either 1 or minus 1 in this case, and that is what we want to show. Okay, we move to the next question. Question number 26. Let A and B be elements of a group and the order of B is 4. It means B to the power 4 is identity, and if A to the power n is equal to B, then find a positive integer k such that A inverse is equal to AK. Okay, since B order of B is equal to 4, this means b to raised power 4 is equal to identity. Also, we know that it is given that a to raised power n is equal to b. If we take the power 4 on both sides, we will get this one. Okay, and on the left side we will have a to raised power 4n, and on the right side, because b4 is actually identity, so instead of b4 we put the identity. Okay, now we can write a to raised power 4n minus 1 plus 1 is equal to identity. I have added and subtracted 1, and this can be written as a is equal to 4n minus 1 into a is equal to e. We can see that with this element a, we have multiplied another element a to raised power 4n minus 1, and we get the identity. This means a inverse is actually equal to a to raised power 4n minus 1, and this means the required k is equal to 4n minus 1. Okay, we move to the next question. The question number 27. The statement is that show that the unitary group U14 can be generated by 3 and also it can be generated by 5. Hence, unitary group under multiplication modulo 14 is cyclic. Is the unitary group U14 can be generated with the element 11. The second part is show that the unitary group under multiplication modulo 20 cannot be generated for any k in that group, and that means unitary group under multiplication modulo 20 is not cyclic. Let's start step by step. We know that the set generated by a means a to raised power n for all n belongs to set of integers. Alright, and the unitary group U14 is the set consisting of elements or consisting of positive integers x belongs to n such that these x are greater or equal to 1 but strictly less than 14, and the condition is that GCD of that x with 14 is equal to 1. And if we check one by one all the elements which are less than 14, we get this unitary group U14 to be 1, 3, 5, 9, 11 and 13. Okay. Clearly, the order of unitary group under multiplication modulo 14 is 6 because there are 6 elements in this group. Now, a group is cyclic if it has an element which has the order equal to the order of group, means that set or that group can be generated by that single element. Okay. Now, I write the statement. Now, if a group G is generated by an element, this means the order of A, that element, and the order of G are actually same. Now we have to show that order of this 3 is equal to 6 because we want to show that unitary group under multiplication modulo 14 is generated by 3 and the order of unitary group is 6. So if we are able to show that the order of 3 is 6, then we have done. Okay. Now 3 square, that is 9 under mod 14. We multiply 3 on both sides, we will get 3 cube, and on the right side it is 27, which is actually congruent to 13 mod 14. Again we multiply 3 on both sides, that is 3 to the power 4, and with 13 when we will multiply by 3, this is 39, and that is congruent to 11 mod 14. We continue in this way. We multiply again 3 on both sides. We will get 3 to the power 5 on the left side, and on the right side it is 33, which is congruent to 5 mod 14. And again, if we take the power of 3 is 6, and on the right side it is 15, and which is congruent to 1 mod 14. This means the order of 3 is equal to 6, and hence the unitary group U14 is generated by 3, and that is what we want to show. Okay, now we have to show that this unitary group under multiplication modulo 14 can be generated by 5 as well. And here we will refer another result. If a group G is cyclic and generated by A, then also this means G is generated by A inverse, means the group generated by an element and the group generated by the inverse of that element are actually the same. Okay, clearly if we see 5 into 3, which is equal to 15, is congruent to 1 mod 14. This means 3 inverse is actually 5. We know that the unitary group under multiplication modulo 14 is generated by 3, so it is obviously generated by 3 inverse, and we know that 3 inverse in that particular group is 5. Now we have to check that unitary group under multiplication modulo 14 can be generated with 11 or not. This is the next part of the question. Okay, we take 11 square, it is 121, and that is congruent to 9 mod 14, and now we multiply both sides with 11 and we will get this 99, and that will be congruent to 1 mod 14. This means the order of 11 is 3, which is not actually the order of the group. This means the unitary group under multiplication modulo 14 cannot be generated by 11. Now we move to the next part of the question, which is about the unitary group under multiplication modulo 20. We know that the unitary group under multiplication modulo 20 consists of the positive integers x such that these x are greater or equal to 1 but strictly less than 20, and GCD of x and 20 should be 1. So if we check all the positive integers which are smaller than 20 1 by 1, we will get this unitary group will be 1, 3, 7, 9, 11, 13, 17 and 19. Okay, now we can check the order of all the elements. The order of 1, which is identity, is 1. The order of 3 is 4, and we know that the order of an element and the order of its inverse are same, and 3 inverse is actually 7. Therefore the order of 7 is also 4. Now the order of 9 is 2, and 9 is inverse of itself. The order of 11 is also 2, because 11 square is 121 and 121 is congruent to 1 mod 20, and the inverse of 11 is also 11. The order of 13 and its inverse, which is actually 17, is equal to 4, and the order of 19 is equal to 2. we have checked all the elements and all the elements have order 1, 2 or 4, but we can see that the order of unitary group under multiplication modulo 20 is 8. So this means unitary group under multiplication modulo 20 cannot be generated with any integer k such that this k belongs to this group, and hence unitary group under multiplication modulo 20 is not cyclic. That's all about today's video. Please like the video and subscribe the channel.